Section 4.8, Video 3, Probability Trees and Binomial Experiment. In this video, we will cover the following objective: use binomial experiment to calculate probabilities. Let's introduce binomial experiment. Consider Part A from Example 2, where a bag of marbles contained 5 blue marbles and 3 white marbles, and our goal was to find the probability of 2 blue marbles. We found every branch that had 2 blue marbles, and we added their probabilities together to get a total of 225 out of 512 for our total probability. This was in Video 1 of Section 4.8, if you'd like to go back and review it. What I'd like to notice about all of these branches is that because we were working with replacement, the marble was looked at and placed back into the bag. Every time you look at a blue branch, the probability is 5/8. And every time you look at a white branch, the probability is 3/8. So another way to calculate this would be to consider the number of combinations or the number of branches that have 2 blue marbles and 1 white marble. So in this case, it would be a combination that out of 3 marbles total, we want 2 to be blue. Then we would also have each one of those branches, so that tells us that there are 3 branches, 1, 2, 3, that met our description. Each one of those branches contains the factors of 2 blue marbles. In this case, here's the blue and here's the blue. However, in this scenario, here's the blue and here's the blue. So we have 2 blue marble branches each time. So we have 2 factors of 5/8. We also have 1 branch that's a white marble, and the probability of the white marble is 3/8. And if we calculate combination of 3, choose 2 marbles to be blue, gave us 3 branches. The probability of 2 blue marbles is 5/8 squared times the probability of 1 branch being white, 3/8. We end up with the same answer of 225 out of 512. Let's take a look at another way to calculate that same problem. A binomial experiment is an experiment with 2 distinct outcomes. The experiment is repeated a finite number of times, and each trial is independent of the other trials. 4 criteria must be met to calculate the probability using binomial experiment. The experiment must have 2 distinct mutually exclusive outcomes. In the previous example, we were looking at choosing a blue marble and choosing something that was not blue. And sometimes these can be categorized as success and failure. So choosing the blue marble was considered success, and then choosing not the blue marble was failure. The experiment is repeated a finite number of trials. Each trial, the probability of success remains the same, and each trial is independent of the other trials. So with criteria 3 and 4, it was important that we had replacement of the marble back into the bag to make sure that the probability of choosing 1 marble didn't affect the others, and that the probability of blue remained 5/8 throughout the problem. To calculate the binomial experiment, we have probability of success designated as variable P, probability failure as variable Q. There are n repeated trials. So to find our successes, in our case we were looking at 2 blues, so 2 successes out of 3 trials. Then we found the combination. We took our probability of success and we used the exponent of 2 because we wanted 2 successes, 2 blues. And we took the probability of failure, probability of white, and we used the exponent of 1 because we wanted 3 total minus 2 blues to equal 1 remaining marble being white. Let's take a look at example 5. A single die is rolled 5 times. find the probability of rolling a 1 4 times. So we have probability of rolling a 1 is 1/6. That's going to be our success. We're going to repeat 5 times, and we're hoping for 4 successes. So we can start out with the probability of a success is 1/6, and we want to repeat that 4 times. We also have the probability of not being successful, 5/6, excuse me, 5/6, and we want that to occur if we have 5 total times and we have 4 times that we roll a 1, we want that to occur once. So notice those exponents total up to our 5 repeated trials. Probability of success will happen 4 times, and probability of not being successful will happen once. The one piece that we still need to fill in is our combination. Out of 5 repeated trials, we wanted 4 successes. Calculating each one of these, we end up with combination of 5 choose 4 means we would have 5 branches total that meet our criteria, and each branch would have these factors. If we take 1/6 to the 4th power, we get 1 out of 1,296. If we take 5/6 to the 1st power, we have 5/6. And remember that 5 would be 5 over 1. That gives us a total of 25 out of 7,776 for our final answer. If you wanted to make this into a decimal, you could. It would be approximately 0.003 or approximately 0.3%. So if you were rolling a die 5 times, the probability of rolling a 1 4 times would be about 0.3%, or 25 out of 7,776. Example 6. Amir has 6 multiple choice questions. Each question has 5 choices. If Amir is guessing, find the probability that he answers 4 questions correctly. Since there are 6 multiple choice questions, we're actually repeating the experiment 6 times. Each question is its own response. The probability of success means you get the question right. So getting the question right, there's 1 right answer, and since there are 5 choices, 1 out of the 5 choices is correct. And we want to get that 1 correct answer 4 times. The probability of not getting the right answer is the other 4/5, and that would happen if we have 6 repeated questions. That would happen twice. 4 are correct and 2 are incorrect. And then we would have a combination out of 6 total questions. We're looking at what is the probability of getting 4 of them correct. Calculating combination of 6 choose 4 would be 15. 1/5 to the 4th power would be 1 out of 625, and 4/5 squared would be 16 out of 25. And that gives us a total of 240 out of 15,625. If we wanted to go to a decimal, we could have 0.01536 or about 1.5%. Question 7. Amir has 6 multiple choice questions. Each question has 5 choices. If Amir is guessing, find the probability that he answers at least 4 questions correctly. So if we want at least 4 questions correctly, we're going to have to find the probability that they get 4 questions correct, plus the probability that they get 5 questions correct, plus the probability that they get all 6 questions correct. Well, we were just looking at the probability of 4 questions correct, and that gave us a combination out of 6 questions, get 4 right. If there are 5 choices, 1 out of the 5 are correct, and we need to repeat that 4 times. And 4 out of the 5 are incorrect, and that needs to be repeated twice. And that gave us a total of 240 out of 15,625. To get 5 correct, we could follow that same pattern. With our combination, out of 6 questions, we want 5 correct. A correct response has a probability of 1/5, and that needs to be repeated 5 times. And an incorrect response has a probability of 4/5, and that needs to be repeated once. Here, combination of 6 choose 5 is 6 times 1 out of 3,125 times 4/5. And that gives a total of 24, remember that 6 is in the numerator, out of 15,625. And we still had 240 out of 15,625 from choosing 4 correct. Now choosing 5 correct, let's finish and get the 6 correct. We have a combination that out of 6 questions get all 6 right. Probability of success is 1 answer out of 5 is correct, and repeat that 6 times. The probability of failure is 4/5, and we're going to repeat that 0 times. Remember that anything to the 0 power is a 1. So that multiplying by 4/5 to the 0 power isn't changing the rest of our work. Combination of 6 choose 6 is 1. And 1/5 to the 6th power is 1 out of 15,625 times 1, for a total of 1 out of 15,625 to get all 6 questions correct. To get at least 4 questions correct, we're going to put the 4 correct, 5 correct, and 6 correct all together because they all meet that description. So finding their sum increases our probability, and we get a total of 265 out of 15,625, or reducing 53 out of 3,125. If you wanted to write this as a decimal, we could take 53 divided by 3,125 and get 0.01696, or 1,696 ten-thousandths, which is about equal to 1.7%. And that ends example 7.